In this video, we're going to continue looking at how we solve for missing side lengths of similar figures, and then we're also going to use our knowledge of similar figures to determine if two triangles or two figures are similar. So let's review our knowledge of similar figures by solving the triangle that you see here currently on the screen. So here you can see we have a triangle within a triangle, and if you think about what we've done in the past, this is a situation where we've actually redrawn the triangles separately. So here I see that my first triangle is the triangle AED. I can use the letters up here to help me trace through it. So I have little triangle AED, so I'm going to draw that over here. Triangle AED. And then if I look at the various side lengths, this side length here is 3, this side length here is x, and this side length here is 2. So that's a pretty easy triangle to redraw. So I have my little one drawn right there. Then my second triangle is triangle A up to C to B. So it's that triangle there in blue. So it's quite a bit bigger. And that's triangle A, C, B. So from here I need to label the side lengths of this triangle as well. This top side length up here is pretty simple. That's 12. Then along this side length A to B, I see that I have two numbers. Remember, we're adding those together. So 2 plus 4 makes this side length here 6. And then this side length over here, again, we're adding those together. So that is the side length with a length of y plus 3. So here I now have my two triangles drawn out separately. And then I just need to decide which triangle is triangle 1. So I'm going to make this triangle 1 and this triangle 2. So now what we're going to do is we're going to draw out our three ratios so that we can then use these ratios to solve for missing side lengths later on. So what I'm going to start with is I'm just going to start with my similarity statement. And I notice that AE and AC are similar. So I have AE here and AC here. So I can write a ratio for those two side lengths. I'm going to do triangle 1 over triangle 2. So I have the ratio of 3 over y plus 3. And then if I look at my next part of my similarity statement, I have ED and CB. So ED and CB. And those, again, we're doing triangle 1 over triangle 2. So I have x over 12 as my ratio. And then my third side length here is that remaining side length of DA and BA. So I have DA and BA. And again, I do triangle 1 over triangle 2. So I have 2 over 6. I know it looks like a B, but that's actually a 6. So now from here, I'm going to move forward and start to find my missing variables using those three ratios that I see right here. So the first one I'm going to look for is I'm going to solve for y. That's just what I'm going to pick first. So I'm going to pick to use the ratio for 3 over y plus 3. And I'm going to pick the ratio of 2 over 6 because that one consists of two numbers. And then I will set them equal and use my knowledge of the cross product here to solve. Now because I have y plus 3, remember we want to put parentheses down there around the y plus 3. And then I'm going to cross multiply here. So we have 3 times 6 is equal to, we've got these two times each other, so it's y plus 3 times 2. So we have 18 on this side. Then if you want to put the 2 in the front, you can do that here. And then we distribute. So we have 18 is equal to 2y plus 6. Subtract 6, subtract 6. So that's 12 is equal to 2y. Divide by 2. And we find that y is equal to 6. So what that's telling us here is this y is equal to 6, which means this entire side length is 6 plus 3, which then is 9, which seems to make sense given how that triangle looks. So now that I've found one value, I'm going to move on and I'm going to find my other variable value. So here now we're going to focus on finding x. So we're going to use x over 12 as one of our ratios because that contains x. And then again, I'm going to use 2 over 6 because that is using a ratio with two numbers. So now that I have a proportion here, I can solve that proportion using cross product. So we have x times 6 is equal to 2 times 12. So we have 6x is equal to 24. Divide both sides by 6, and we find x is equal to 4, which if you look at this picture up here, this would be 4, so this would be 4. That seems to make sense. And then if I even look closely, 2 times 3 is 6. 3 times 3 is 9. 4 times 3 is 12. So this big triangle is basically 3 times the small triangle. And so I can see that in a couple different ways. Not only does that pattern appear once I find all of the sides, but it's a pattern that I can see directly in my triangles. So now what we're going to do is we're actually going to do this whole process backwards. We're trying to figure out, are these two quadrilaterals similar? So this is like our question. You can see I wrote it at the top. Is quadrilateral SPQR similar to quadrilateral ZWXY? It's my goal to figure out if that is in fact a true statement. So what I'm going to do here is I'm going to pair up what seem to be my corresponding sides and see if they have equivalent ratios. So here, this is what I'm thinking is my similar figure. So I'm thinking that S and P aligns with Z and W. I'm then thinking P and Q aligns with W and X. I'm thinking Q and R aligns with X and Y. And I'm thinking S and R aligns with Z and Y. That's what I'm thinking is going to happen. And as a result of that, what I need to check is I need to check and see if those corresponding side lengths have similar ratios. And they have ratios that simplify down to the exact same number. So here, remember this is quadrilateral 1 and this is quadrilateral 2. I'm going to make two ratios. So I can see I have 14 over 9 as one ratio, and I need to determine what that equals. And then I have 6 over 3 with my other paired up side length. Now I know that 6 over 3 is 2, and then if I take my calculator and I divide 14 by 9, I find 1.56. So we know that if we have similar figures, that these ratios actually have to equal the exact same number. Unfortunately, they do not. So what we're seeing here when we pair up what we think are those corresponding sides, and if we see that they do not have side lengths that have ratios that are the same, they are in fact not similar. So here we would say that quadrilateral SPQR is not similar to quadrilateral ZWXY. And we can see that it's not similar to quadrilateral ZWXY because their side ratios are not the same. So there we have it. So we can do this both forwards, finding those missing side lengths, and backwards, justify whether or not we have similar figures. So here we have another pair of shapes, and our goal is again to determine, are these two triangles similar? So what I'm going to do first is pair up what I think are my corresponding sides. So I think that corresponding sides are 8 and 4, 20 and 12, and X and Z and A and B. So those are what I think are corresponding. Now remember, in order to check these, I need to actually pair up those side lengths and check that they have, again, those ratios that are in fact similar. So here, if we pair up 8 and 4, so we have 8 over 4. I know that's going to simplify down to 2. If I then look at 20 and 12, and then I divide 20 by 12, I get 1.67. So here I'm noticing, okay, when I paired up my corresponding side lengths and found their side ratios, they are not the same. So even though these triangles look like they would be similar, since these side ratios are not the same, they are not similar triangles. So as a result, we need to say that in our similarity statement. So here we're going to practice naming our triangles. Remember, we want to go in the same order. So I'm going to do triangle, I'm going to do X, Z, Y. So name them in the same order. X, Z, Y is not similar to triangle A, B, C. And remember, those orders matter because we want to pair up those angles in that similarity statement because their side ratios are not the same. And here, I mean, the big thing is you want to have these numbers justified in your work and relating directly to that similarity statement of whether or not they are similar or not at the bottom. So make sure you have all your work shown so that you can truly justify, yes, these two shapes are similar, or no, they are not. So in our last example here, we have two triangles again, and this time we actually have 3 side lengths. We're going to have to check all of the side lengths to see if we do in fact have similar figures. So let's start by pairing up the sides that we think are corresponding. So I have R and T, X and Z, S and T, and Z and Y, R and S, and X and Y. So now that we have those paired up, let's write our ratios for these, and then we can calculate the values of our ratios. So we have triangle 1 over triangle 2, so we have 6 over 18. Then I have 5 over 15 and 4 over 12. And if I take 6 over 18 in my calculator and divide that out, what I find is that I get 0.33. 5 over 15, I get 0.33. And 4 over 12, I get 0.33. So what I'm noticing here is that unlike the previous examples that we've seen, all of these side ratio pairs are resulting in the exact same value. They're all resulting in 0.33. And really, truly, if we look at these, we can see that 6 over 18 would simplify to a third, 5 over 15 would simplify to a third, and 4 over 12 would simplify to a third. So that makes sense. But what this is also showing us is that we do in fact have similar figures here because this big triangle is just 3 times bigger than that small triangle. Otherwise, it's the exact same general proportional shape. So our last step here is to write our similarity statement. And again, remember, we need to go in the same order as we name our shapes. So I'm going to say triangle, make my little triangle there, RTS. That's the order I'm going to go in, RTS. Is similar to, that's the is similar to symbol there. That's what that little tilde squiggle is. Triangle XZY. And I can see that XZY. So I can say that they are similar because their corresponding, running out of space there, corresponding side ratios all equal 0.33. So because all of these corresponding side ratios are the same, we can state with certainty that these two figures are in fact similar figures.